Right, hello everyone, and a massive welcome to all our 10th to 12th standard students tuning in. I'm absolutely thrilled to have you here for this ultimate explainer on mastering chemistry calculations. You know, if you've ever felt completely overwhelmed by stoichiometry, trust me, you are in exactly the right place. Today we're going to break the whole thing down so completely that you'll be walking into your exams with absolute confidence. Oh, and real quick, do make sure to pop the captions on. They're a brilliant little tool to help you follow along and take notes as we go. Right, let's dive straight in, shall we?
So here's our masterclass journey for today. We'll start by demystifying the mole concept, then look at the chemical recipe, and follow the mole roadmap. After that, we'll master BCA tables, tackle limiting reactants, and finish up by beating those really common exam traps.
Okay, part 1. Demystifying the mole concept. Now, before we actually calculate anything, we kind of need to unlearn a pretty massive misconception. The mole concept is actually incredibly simple once you strip away all those intimidating numbers. Look, the mole is literally nothing more than a counting unit. It's just a word that represents a specific, albeit absolutely massive, number. 6.02 times 10 to the power of 23. We call this Avogadro's constant. So why do chemists use it? Well, because atoms and molecules are unbelievably small. We obviously can't pop a single atom on a lab scale, but we can absolutely measure out a whole mole of them. It's essentially the bridge between the invisible microscopic world and the measurable stuff we actually see in the lab.
Think of it this way. If I asked you to go buy a dozen eggs, you instantly know to get 12, right? If I say a dozen cars, well, that's 12 cars. A dozen just means 12 no matter what you're counting. And honestly, the mole works exactly the same way. There's this classic O-level trap where students think 1 mole means 1 molecule. Nope, no way. 1 mole just means an exact quantity of particles. So 1 mole of water? That is 6.02 times 10 to the power of 23 molecules of water. A mole of copper? Exactly the same vast number, just in copper atoms. It's just a huge dozen, really.
Right then, moving on to part 2, the chemical recipe.
Let's see how this actually applies to chemistry. Because at the end of the day, chemistry is basically just a highly precise form of cooking. Say you're baking a cake. Your recipe might need 2 cups of flour and 1 cup of sugar to make exactly 1 cake. Well, a balanced chemical equation does the exact same thing for a chemical reaction. Those big numbers sitting in front of the chemical formulas, the coefficients, they tell you the precise ratio of ingredients you need. But here is the absolute most crucial bit. Those coefficients tell us how many moles we need, not how much mass in grams. You literally cannot read a chemical equation in grams. It always has to be read in moles.
And that brings us to a word that honestly terrifies a lot of students: stoichiometry. But don't panic. Stoichiometry is literally just the mathematical framework that safely gets us from our theoretical chemical recipe to real-world measurements. It's just the process of converting what you have into what you need, using that balanced equation as your trusty guide.
Which perfectly lines up part 3, the mole roadmap.
To make stoichiometry an absolute breeze, we use this ultimate navigation system. Seriously, whenever you're given the mass of a starting chemical and asked to find the mass of a product, you just follow this exact 3-step route. Step 1, take the mass of the chemical you know and convert it into moles by dividing by its molar mass. Remember, we have to get into moles because, well, that's the language the equation speaks. Step 2, apply the mole ratio. This is where you grab those big coefficients from your balanced equation to find the ratio between your starting stuff and your target. And finally, step 3, convert those newly found moles into your target unit, which is usually done by multiplying by the molar mass of the new chemical to get grams. Easy as pie.
But here's a bit of a question for you. When a reaction is actually bubbling away, reactants are disappearing, products are appearing, the amounts are constantly shifting around. So how exactly do we track these changing mole amounts systematically without getting totally lost in a sea of maths? That brings us to part 4, mastering BCA tables. Okay, so here is your absolute secret weapon for exam success. BCA. It stands for before, change, after. You write your balanced equation right at the top. Underneath that, you create 3 rows. The before row is exactly what you start with in the beaker. The change row shows the actual chemical reaction taking place, and keep a really close eye on this. Reactants get a minus sign because they're being used up, and products get a plus sign because they're being created. Finally, the after row is just the simple maths of before combined with change. It tells you exactly what is sitting in your beaker the moment the reaction stops.
Now, to use these BCA tables properly, you absolutely must follow these golden rules.
First, balance the equation. If your recipe's wrong, the cake's gonna fail, right? Second, and I cannot stress this enough, you can only put moles into a BCA table. If an exam question throws grams or a volume of gas at you, you have to convert it to moles first. No exceptions. Third, the change row is strictly dictated by the coefficients, the mole ratio, from your balanced equation. If you stick to these rules, your calculations will literally organize themselves.
All right, let's level up. Part 5, Limiting Reactants and Yield.
Now that we've got our tracking system sorted, we're ready for the actual boss battle of stoichiometry. Let's jump back to that kitchen analogy for a sec. Imagine you're baking that cake again. You've got 10 massive bags of flour, 20 bags of sugar, but you only have 2 eggs. What happens?
Well, you have to stop baking. You can literally only make as much cake as those 2 little eggs will allow. In chemistry, those eggs are what we call your limiting reactant. It's the substance that gets completely consumed first. The very second it runs out, the reaction violently stops, and that dictates the absolute maximum amount of product you can possibly make. And all that extra flour and sugar, we call that the excess reactant. It just sits there in the beaker, left over, doing absolutely nothing.
Once we've spotted our limiting reactant, we can figure out our yield. But listen, there are 2 types of yield you really need to know. Theoretical yield is the perfect, ideal world of maths. It's the maximum amount of product you calculate on paper based on your limiting reactant. Experimental yield, or actual yield, on the other hand, is the messy reality of the laboratory. It's what you actually manage to scrape out of the bottom of the beaker at the end of the day. In the real world, you might spill a drop or a side reaction kicks in, which means your experimental yield is almost always going to be lower than your theoretical yield.
So, to measure how efficient our reaction actually was, we calculate the percentage yield. It's just the experimental yield divided by the theoretical yield, all multiplied by 100. Definitely write this formula down. Oh, and here is a massive tip to self-check your work in an exam. Percentage yield can never, ever exceed 100%. It's impossible. If you get 110%, just stop. You've either picked the wrong limiting reactant or you've accidentally put the theoretical yield on the top of your fraction. Easy mistake, but a costly one.
Right, final section, Part 6, Beating Common Exam Traps.
Let's turn all this theory into actual exam marks by avoiding the things that drive examiners crazy. First up, treating the molar ratio as 1-to-1 when the balanced equation clearly says otherwise. That completely ruins the whole calculation. Always check those coefficients. Second, rounding your numbers too early. Please keep the full messy number in your calculator right until the very final step, or you'll get hit with rounding errors. Third, mixing up centimeters cubed and decimeters cubed in concentration questions. Honestly, just write divide by 1,000 on your exam paper the very second you spot cm cubed. And finally, the fatal error, calculating your product yield using the excess reactant instead of the limiting one. Don't fall for it.
To guarantee those top marks, just follow this foolproof 4-step process every single time. Step 1. Write out and double-check your balanced equation. Step 2. Convert whatever weird unit they give you straight into moles. Step 3. Use the mole ratio to spot your limiting reactant. And Step 4. Calculate your theoretical yield purely from that limiting reactant. If you stick to this structured path and maybe use a BCA table to organize your thoughts, your calculations will stay perfectly on track every time.
And just like that, we've reached the end of our explainer. You now have the exact roadmap you need to conquer stoichiometry. Just remember, it's all about finding the moles, applying the ratio, and staying super organized. Please do follow our social media accounts for more brilliant updates and explainers just like this one. Also, have a quick glance at the ticker at the bottom of your screen right now. Academic Zenith Online Academy is actually offering a massive 30% discount on any course when you book a free demo class, so definitely check that out. But before you log off, I want you to think about this. If we can predict the exact yield of a reaction flawlessly on paper, why do industrial chemists spend millions of pounds just trying to improve experimental yields by a fraction of a percent? Keep practicing those calculations, stay curious, and I'll see you in the next one.
Cheers.